It is our pleasure to welcome Oleg Lazarev from Harvard, about inverting primes and Weinstein geometry.
Yeah, thank you for the invitation. Let me just first say that the results in this talk are joint work with Zach Sullivan and Hiro Lee Tanaka. So before talking about the symplectic case of inverting primes, let me begin by reviewing some analogs in topology. And this is what's called localization. So in topology, there's a functor for any set of primes P going from spaces to spaces. And this functor was investigated by Sullivan, Quillen, probably lots of other people before them, but they're the ones who really pushed the theory forward in rational homotopy theory. By spaces, I mean CW complexes up to homotopy, and I also take simply connected ones. And the main property of this functor is that they localize invariance. So the singular cohomology of x sub p with z coefficients is the localization of the singular homology of x away from the set of primes p. So you just tensor this abelian group with z with p inverted. Okay. So this functor is a geometric version of this localization of modules. Okay. This construction of this xp actually depends on the starting CW presentation of x. Basically, you replace all the cells in the CW presentation with what's called p cells. But then you prove a posteriori that the resulting homotopy type of x of p is actually independent of the Weinstein presentation, or sorry, the CW presentation of x that you started with. And the last property is that this functor is idempotent. So if you apply it twice, that's the same thing as applying it once. And this is just the geometric analog of the fact that if you take a Z module, you invert P twice, that's the same thing as inverting P once. Okay. So here's just an example to see that these spaces are not so complicated. This P localization of a circle is this mapping telescope. Where you just attach a circle to a circle by a map that winds P times around. Okay, and feel free to stop me at any point. I'm going to try to keep my eye on the chat, but I might miss something. Okay, so that's the classical story. And now we want to do this in symplectic topology. So we want to develop a theory of symplectic localization. And ideally, we would have a theory that satisfies some versions of these three properties, namely that invariance, localize, that the construction can be explicit in that it depends on some kind of presentation, but is actually independent of the presentation, and it's idempotent. Okay, so first we need a symplectic analog of what a CW complex is, and that's just a Weinstein domain. So let me say what a Weinstein domain is. So basically, it's what you get by starting with a standard symplectic ball, and then attaching handles along isotropic attaching spheres. Now, some of those handles, so this isotropic condition forces the handles to have index at most n. Some of those handles have index strictly less than n, and those are called subcritical. And these handles are essentially topological. they satisfy an H principal, so they're not so interesting from the symplectic point of view. And then there's some critical handles of index equal to n. And the important thing about those handles is that they have cocores here, which are Lagrangian. So these cocores are Lagrangian. And a lot of the symplectic information of the whole symplectic manifold can actually just be read off from J holomorphic curve invariance of just those cocores. Okay, but it's some decomposition of your symplectic manifold, and there's these subcritical and critical handles, and the critical handles are the most important. Okay, so now let me give the first result indicating that some kind of symplectic localization phenomenon occurs. And this is, so P is going to be a set of primes, and this is going to be a theorem of Abu-Zaid and Seidel. They showed that given a Weinstein domain X of dimension 2n, where n is at least 6, there exists another Weinstein domain, X sub P, which is diffeomorphic to X, and its symplectic cohomology is the localization of the symplectic cohomology of X away from P. So it has the property that the invariants localize as desired. And the idea of their construction is to start with some Lefschetz fibration for X. This Lefschetz fibration comes with a collection of vanishing cycles, and then they modify the vanishing cycles in some way. So although this construction satisfies the first property, desired in localization, it doesn't satisfy the other two, so at least not in a way that's clear. So it's not clear if X sub P is independent of the Lefschetz fibration / Weinstein presentation of X, because what you do is you pick some Lefschetz fibration, then you do something to the vanishing cycles. It's not clear if you pick another Lefschetz vibration, maybe you'll get a completely different thing. And it's also not clear if it's idempotent from their construction. But at least the first property is satisfied. So this is a good indication. Something interesting is going on. Any questions so far?
Yes. The cohomology condition is like is analogous to the homology identity in the topological context. The condition that XP is diffeomorphic to X, what is that analogous to? Or is it just a way to say it's maybe a reasonable candidate?
It's so Abu-Zaid and Seidel were interested in constructing these exotic symplectic manifolds. So examples that were indistinguishable from, so X and XP are indistinguishable from the point of view of smooth topology, but their symplectic topology is different. I mean, so in some sense, yes, it's a good candidate. I mean, if you create something that's like not even diffeomorphic to X, like what are you creating? You're creating some other completely random manifold. So there's some link between X and XP.
So they have a common characteristic of having the same structure, but then what is, in the topological context, what's the analog of that? So they're different. I just have very little knowledge in localization.
Yeah, there's no analog, I would say.
Okay, so it's just another layer because you're moving to
because symplectic geometry has.
Sorry.
That's right. That's right.
Okay, thank you.
Yeah.
So maybe she was asking the same question, but like XPP is the same as XP was a homotopy equivalence claim, right? Or like either of these properties.
Sorry, can you repeat the question?
Or for instance, when XP are independent, when you mean XP is independent of choices, for the spaces, this was a homotopy equivalence statement, right? It wasn't,
right.
That's what Sarah was asking as well. I don't really understand, but so what would the statement?
Oh, what I mean about equivalence in the symplectic case, I mean either symplectomorphism or Weinstein homotopy equivalence, which is stronger than symplectomorphism.
But previously, you only had homotopy equivalence, right?
Right. That's true.
For instance, if you...
so you're in the symplectic world, so all the equivalences should be upgraded to symplectic equivalences.
Can I ask a question? There's one point I don't completely understand, because the homology of X goes into SH of X, or the other way around, it doesn't matter. So I don't understand how XP should be diffeomorphic to X, because when you replace SH of X by SH of X tensor Z of 1 over P, you should also do something probably to the homology of X, and so so XP should not have the same homology as X. In general, I mean, depends which part of the homology goes to something non-zero in SH of X.
So, Claude, I think what's happening is that you have exact sequences relating singular homology and symplectic homology, but the structure at infinity in this new XPs is very different, and so there is no so the singular homology remains the same, but it's perturbed by what happens at infinity, and that's the end in. So maybe Oleg can write it down, but
yes, that's exactly that's what I was thinking. So if you
there's a diagram that commutes like this, and of course SH of X is going to map into SH of X localized.
Yes, that I understand, but
and you still have the.
But Oleg,
does that answer your question?
No, because there is you're writing an isomorphism between H star X and H star XP, which is not true, right?
It has to be true because they're diffeomorphic.
Ah, sorry. Yes, you're right. Absolutely.
That's my issue.
No, but it's correct. When you include it in the other part, that's where the distinction happens. Yes, sure.
Yeah, this right diagonal is an isomorphism, but.
Okay. Oh, okay. Maybe I understand. It's straight.
Yeah, like.
Okay, go ahead. Sorry.
And the point is, these maps are not isomorphisms. These. Yeah, if symplectic homology were isomorphic.
I know they're not isomorphisms. But they also don't have.
So this is the diagram that commutes.
Okay.
Okay. So right. So this was some kind of partial symplectic localization. Let me mention another result in this direction, which is work of Chilibog and Eli Ashberg, building off of some work of Emmy Murphy, that if you start with a Weinstein domain, X of dimension at least 6, there exists what's called a flexible Weinstein domain X sub flex, with the property that it's that it's wrapped Fukaya category is trivial. Again, it's diffeomorphic to X, and furthermore, it satisfies this H principle, namely if X and y are diffeomorphic, then x flex and y flex are actually symplectomorphic. So this flexibilization, it forgets all of the symplectic topology, but it remembers the smooth topology. So let me just say x flex is also diffeomorphic to x. So what this implies is that x flex is independent of the presentation of x, and x flex is idempotent. So, okay, so by equivalence here, I mean symplectomorphism or Weinstein homotopy. Okay. So this flexibilization, it does satisfy all three properties that topological localization did.
Hello, sorry, I have a question. Are you saying for any Weinstein manifold, X is any Weinstein, or it's a specific class? Like if I apply this to the cotangent bundle, the wrap Fukaya category of the cotangent is not trivial, and then I apply this construction, I should get something trivial. Can you describe X flex in the case of the cotangent bundle? Like what is X flex? Do we have some sort of idea?
Yeah, I'll describe it.
Okay.
Yeah, I'll describe it soon.
All right, thank you.
Yep. Okay, but the main point is that this is a candidate localization, but the unfortunate thing is that it kills all symplectic topology, and we would like a theory that generalizes this to the case of an arbitrary prime, kind of building off of what Abzid and Seidel proved. So, and also let me just say that this X flex is a local modification of the attaching spheres. So what do I mean? So let's look at the flexibilization of a cotangent bundle of a sphere. So there, the standard cotangent bundle of a sphere is you start with a ball and you attach a single handle along the Legendrian nut. And this flexibilization procedure, it's a local modification of the attaching spheres. So it adds this zigzag to the attaching spheres, and this is what's called a loose chart. So adding this loose chart, it forces symplectic homology actually to be 0. So that's what flexibilization is. Now, what I want to point out is that there's another thing you can do. You could first Weinstein homotope the standard presentation by adding 2 extra handles. So these are some handle moves, and these are symplectomorphic. Then I can apply the flexibilization to that new presentation. So I add loose charts to these 2 handles, and then I can, okay, this thing on the bottom right is actually homotopic to a presentation with 1 handle, and now two of these loose charts. So on the upper top, I have a presentation with 1 loose chart. On the bottom, I have a resulting presentation with 2 loose charts. And I would like for this theory to be well defined, I would want these to be Weinstein homotopic because the original 2 things were Weinstein homotopic. And this is in fact true. These are also Weinstein homotopic by the H principle. So these are Weinstein homotopic by Murphy's H principle. Basically, whenever you have Legendrians with loose charts that are smoothly isotopic, plus a little bit of tangential data, they will be Legendrian isotopic. So the point is that this invariance under Weinstein homotopy of flexibilization is essentially equivalent to some kind of H principle. And so you could play this game for like any kind of local modification. You just start with attaching spheres, modify them locally in some way, and then just ask if it's Weinstein homotopy equivalent. Now that will not be true in general. However, the point of this talk is that it will hold under some restricted class of new local models. Okay, so that's flexibilization and kind of a description of why it's homotopy invariant, Weinstein homotopy invariant. So the first result I want to talk about is joint work with Zach Sullivan, and this is kind of extending this result of Abu Zaid and Seidel. We showed that given a Weinstein domain X of dimension at least 10, there exists a Weinstein subdomain X sub P inside X, which is diffeomorphic to X, with the property that it localizes invariant. So we showed that the Rapp-Foucault category of this X sub P is the localization of the Rapp-Foucault category of X. So this is a little bit stronger than what Abu Zaid and Seidel proved, because they only did the level, the isomorphism on the level of symplectic homology. This is upgrading it to the Foucault category level. But I would say that the main point here is that we actually show that X sub P is a Weinstein subdomain. So it's actually sitting inside of X, whereas in Abu Zaid and Seidel, X and X sub P were not, it was not clear how they were related. And by Weinstein subdomain, you should think singular Lagrangian, because any Weinstein domain retracts the singular Lagrangian skeleton. So inside X, you have this Weinstein subdomain, which is kind of a singular Lagrangian. So you're asking, what are the singular Lagrangians inside of X? And furthermore, remember, you can do this for sets of primes, that X sub P is going to be sitting inside of X sub Q if P is a set of primes that contains Q, or P contains 0. And furthermore, this construction is a local modification of the attaching spheres, just like in flexibilization. And furthermore, if you take P to be 0, which is going to be a prime for the sake of this talk, then you actually get the flexible Weinstein structure. So let me just do an example that I think will clarify the situation. Let's again go back to the case.
1 over P for P equals 0.
It's 0.
Okay.
So inverting 0 just makes everything trivial. And so remember, so here we have the Foucault category of X with 1 over 0. This is just 0, which is also the Foucault category of the flexibilization.
Okay, thank you.
That's what I meant by that. So this is just a notational formality. So let's start with X, a cotangent bundle of a sphere. It has to be a high dimensional sphere because, as you can guess, there's not a lot of exotic subdomains in T star S1. So sitting inside of that, we have, by construction, the localizations away from 2, away from 3, away from 5, for any other prime. But sitting inside of that, we have localizations at pairs of primes, which I should say is the same thing as, you could also localize at like an integer, which is not a prime, but that's going to be the same thing, at least conjecturally, as localizing at a set of its prime denominators. But anyway, so sitting inside of the 2 and 3 localization is the 2-3 localization. And sitting inside of that is the 2-3-5 localization, which sits inside of the 2-3 and also the 3-5. And finally, at the very bottom of this lattice is sitting the flexible version of T star of a cotangent bundle, which is localization of 0. So the point is, you have this lattice of subdomains of a cotangent bundle, which you should think of as singular Lagrangians. And of course, T star Sn has only one smooth Lagrangian, at least on the level of topology. But it has all these singular Lagrangians, which have interesting floor theoretic invariants.
So,
and Oleg, I should say that
Oleg,
yeah.
Just one question. So, yeah. in the classical homotopy world, you have also a result saying that from all localizations, you can build up by a pullback the initial integral space. I don't know how, this has a name that I forget, but basically if you know the localizations of a space for all primes P, then you can pull back from this information and the localization. You have to know a little bit more. You have to know how they fit into the rationalization of the space. But after that, you can do a pullback diagram, and you it's purely algebraic. You deduce from that the initial space. Is this something like this true here too? Do you know?
I mean, certainly. Okay, I guess I should say that certainly you could start with like the 2 localization and the 3 localization, which agree along the 2-3 localization, and you could kind of glue these subdomains in a way to get the whole cotangent bundle. The issue I would say is that I don't know of a good theory of pulling back in symplectic topology. It
has to be just
because there's,
you know, it's a level.
No, I understand. There's algebraically it's well defined, but it seems like if you try to do it geometrically, it's not well defined because you have 2 domains which agree along one thing, and you have their attaching spheres. You can make them link in different ways, and you can get different domains. I guess what I'm trying to say is there's different ways to glue. There's different ways to glue 2 domains along a subdomain, and that is a source of confusion to me. But certainly there is one way to glue this 2 localization, this 3 localization,
what I meant
to get the whole thing.
What I meant was more the algebraic side. I mean, you could say I have some maps relating all these localizations, and it's algebraic level that is looking maybe to the Raphokaya category, or maybe to some homologies, maybe because it's easier. And for homologies, you do have some maps into, you know, you have the algebraic object for each prime P, and then you have a map of it into its tensor with the rationals. And then you can do a pullback algebraically. And the result is something. It's an algebraic object. The question is that algebraic object the respective functor applied to the to X, to the initial X. It's an integral gadget. You see, that's a whole. But yeah, basically that's what I'm saying. You know.
Can I make a comment? Oleg, is it okay if I jump in here? Okay, yeah. So I think what Octave is referring to is the arithmetic fracture square, and that's a slightly different context for 2 reasons. One is because that actually has to do with P completions, not P localizations. And so one of the ingredients that I think is still missing in the symplectic world is actually how to complete at an ideal rather than just inverting an ideal. And as you know, completing is a pretty delicate process. And the other is, I think Octave's, the answer to Octave's question, I think modulus unfiniteness hypotheses is somehow algebraically true, mainly because I think there's a general principle that spec of the integers is covered by, you know, adels of all the primes and also by the rationals. Right. And so somehow, like algebraically, there should be something tautological that has nothing to do with symplectic geometry.
What Oleg wrote there, this diagram that he wrote, it kind of tells me exactly what I was saying. So if this what you wrote is true, then I'm already kind of happy. I was happy before, but I'm happier.
Yeah. This is definitely a fiber square of categories, like a pullback square of categories. But I think there's some geometric complications. But yes, something like that is going to be true. Okay, and so you have this lattice of subdomains in a cotangent bundle. I want to say briefly that, in fact, the order of this lattice cannot be reversed. This is a pretty rigid lattice in the sense that you cannot, for example, symplectically embed this like 2 localization of a cotangent bundle inside the 2-3 localization, even though the 2, 3 one goes into the 2 localization. Because if you had that, then you would have this Viterbo ring map on SH going from the bigger domain to the smaller domain, and you could apply it at with coefficients, say Z mod 3, and this this SH on the left, it will be 0 because well you're inverting 3, but you're also looking with Z mod 3 coefficients, so that's 0. Whereas the SH on the right, you inverted 2, and you're looking with Z mod 3 coefficients, but 2 is already invertible in Z mod 3, and so that's in fact the same thing as just SH of the original domain with Z mod 3 coefficients, and that is non-zero, and there's no unidal ring map from the 0 ring to a non-zero ring, so this is impossible. So I'm just saying that you can't, one subdomain sits inside the other, but the other one could not be symplectically embedded into the first one. Okay. So let me keep going. So we have all these subdomains in T star Sn. Now let me state a result with Zach Sullivan, which is that if M is simply connected in spin, then in fact, any Weinstein subdomain X of T star M has the same wrapped Fukaya category as one of these prime localizations for some sets of primes P. So at least Floor theoretically, any subdomain is one of these for cotangent bundles. And of course, this is not true in general, that any subdomain X naught of X has the wrapped Fukaya category of X naught isomorphic to the wrapped Fukaya category of X localized at some primes. So this is some extra rigidity for cotangent bundles. So some kind of classification of singular Lagrangians, like the classification of smooth Lagrangians that we have in some form currently. Yeah. So just to give an example, like the silly example, one silly example is just take a cotangent bundle of N inside the boundary connect sum of a cotangent bundle of N with cotangent bundle of M. Cotangent bundle of N is not a prime localization of the bigger subdomain. You can check that. Okay, so far I've talked about basically the first property of topological localization, which is that getting an operation which localizes the algebraic invariance. But I haven't really said anything about the other two properties, which is basically this homotopy invariance of presentation and also the idempotency. So how unique is this XP that we've constructed? Let me mention two symplectically trivial operations, which are subcritical handle attachments, attaching handles of index at most n. And then there's also stabilization, which is taking x to x times t star d1, which is viewed as a sector. And symplectically trivial, I mean, these operations don't affect the Fukaya category. And I mean, subcriticals also, these are essentially topological, they satisfy an H principle. So it makes sense to consider Weinstein domains up to these two sets of moves. Let me mention a result with Zach Sullivan and Hiroshi Tanaka, which is the following. So suppose you start with X and X prime, which are symplectomorphic, then we prove that XP and X prime P are symplectomorphic up to stabilization and subcritical handles. So you pick two presentations of X, you apply this XP, which a priori depends on the presentation, but you prove a posteriori that it's actually the same up to stabilization and subcriticals. Furthermore, we have idempotency, again, up to stabilization and subcriticals. And we have a form of functoriality for this operation. So in fact, it gives a functor from Weinstein domains up to stabilization and subcriticals to Weinstein domains, stabilization and subcriticals. So this result, I think, should be viewed as some kind of generalization of this result of Chilibek, Liashberg, and Murphy, where they just did the flexible case. And of course, they were able to prove something stronger because all of symplectic topology was thrown away. But in this case, we're doing it for an arbitrary prime, and we're proving it up to stabilization and subcriticals, but we are showing that it is well defined up to these operations. Okay, any questions about this result or the previous classification results I stated?
Well, just a comment, I guess this kind of shows that in this Weinstein category, equivalence should not be up to Weinstein diffeomorphism or symplectomorphism, but up to these things. Like, seems more natural, right? Up to stabilization and attaching subcritical. But, yeah,
right.
I guess that's...
Yeah, we're loosening up the geometry. We're relaxing the notion of equivalence and being able to prove some results there. But I think this is a natural way to relax the conditions because the Fukaya category is not going to be able to see these things at all. And so we would not really have any hope of distinguishing these things from the symplectic point of view anyway.
Yeah, well, it's the same thing as saying we should do up to homotopy equivalence in top and not up to homeomorphism because we can't. But up to homotopy equivalence, there's a bit more hope. So that's good.
Right.
Anyway, just random comment, sorry.
Okay, so
I just want to echo that is actually like one way to look at this work is we do eventually actually construct that localization with respect to exactly what Francois said. So Francois, I just want to echo that's the same observation I think we developed as well eventually.
So we construct some category wine that has like subcriticals inverted and it's a state where we look at stable Weinstein domains. We invert subcriticals and we cook up a functor of that, an endo functor of that. Okay, so those are the results. Let me talk a bit about the actual constructions that go into this. So the basic construction is given a Lagrangian disk in a Weinstein domain with Lagrangian boundary, you can form a subdomain by carving out that disk. So this is it's called carving out. And so we have here the disk. You should think of a Lagrangian disk as the cocore of some handle, and this carved out domain is the result of just removing that handle. And this is a subdomain. And there's a result of Ganatra, Parda, and Shende, which is that if you look at the Rapukai category of the subdomain, where you've carved out the disk D, that's actually equivalent to the Fukai category of X, where you do this categorical localization by the object D. Because remember, D is a Lagrangian cocore, it's an object of the Fukai category. Okay. Oh, and I should say, I keep writing this twa here to denote twisted complexes. So I take the Fukai category of genuine Lagrangians, and then I enlarge it by looking at twisted complexes. So that's going to be important later. But it's some algebraic enlargement of the Fukai category. And furthermore, they showed that the Lagrangian cocores CX generate the Fukai category. So these twisted complexes on arbitrary Lagrangians is isomorphic to just twisted complexes on just the cocores. Okay, so the main takeaway is that one way, in fact, the only way to get subdomains is by looking at Lagrangian disks and carving out those disks, and the Fukaya category of the subdomain can be computed by this Ganatra-Pardon-Shende formula. So we just need a source of Lagrangian disks, and one source of disks are due to Abouzeid and Seidel in their original work that I already mentioned. So their construction is the following. They say, well, given a smooth subdomain U inside an n-1 dimensional sphere, they cook up a n-dimensional Lagrangian disk in the cotangent bundle of Dn, such that that disk is isomorphic to the following twisted complex. So this is some twisted complex. You just take the reduced singular cochains, on U, use just a smooth subdomain, and that's a chain complex, and you tensor that with a cotangent fiber of T star Dn. And so the thing on the left is a genuine Lagrangian, the thing on the right is some twisted complex, but they're isomorphic in the Fukaya category. And let me just briefly say what the construction of this du is. Basically, you pick some function from a disk to R with the condition that this function goes to negative infinity as you move towards the U part of the boundary. So remember, U is sitting inside a sphere, which can be viewed as the boundary of a disk. As you move towards that U, you go to negative infinity. So you have this function that blows up, and you take the differential of that function, and you look at the graph of that, the one form in T star Dn, and that's your disk. That's roughly the construction. Okay, so it's a pretty concrete disk. That's what I'm trying to say. And now the idea is to take U to be a P Moore space inside of n-1. Then this is where you need n to be at least 5, because you need to take this P Moore space and then embed it inside a sphere. And that embedding can only occur if n is at least 5. So this is over here as well. And the reduced singular cochains of this Moore space is just the cone of P, or this chain complex with 2 copies of Z with differential, it's just multiplication by P. And let's call this disk D sub P. So the conclusion is you have this D sub P disk, and it's isomorphic to the cotangent fiber tensor, this chain complex. And then the idea is to carve out this D sub P disk. So this is where our construction starts to deviate from the construction of Abouzeid and Seidel. So the idea is we have X, we have its cocores. So because we fixed the presentation of X.
Sorry to be a bad question, but why is a P Moore space? Why can you view the P Moore space? The P Moore space is a cone between one disk and another disk, right? A disk of dimension maybe I don't know.
It's 5. It's like a circle, and then
a circle, and right. But attached with the multiplication, right? And why is this a disk? So you say that this is a disk at some moment, right? Or I misunderstood something. You embed it as a disk.
So U is not a so U is not a disk. U is just a thickening of a Moore space. Okay. U is homotopy equivalent to a Moore space.
It's all right.
And but then you cook up a function which is on a disk that is asymptotic to like negative infinity along U.
Okay, I got it. I think.
And then you cook up a disk from that.
Okay.
Yeah. Okay. So going back to this carving out procedure, the idea is you fix a presentation for X. You look at the cocores, these CXs, or the critical handles, and the neighborhood of those cocores just look like T star Dn. And you implant these DP disks into there, and then you carve them out. You remove those DP disks, and then then you reattach some flexible handles to this domain in order to get the right topology. So that XP and X are diffeomorphic. But these flexible handles, they don't change the Fukaya category. So essentially, you should just think of just what happens when I remove these DP disks. And so what happens, so here I have a long formula. We're trying to compute the Fukaya category of X sub P. That's the same thing as Fukaya category of X with these disks removed, because we can ignore the flexible handles. By this Ganatra-Pardon-Shende formula, that's just the localization by one of these DP disks. The DP disk is this chain complex, this cone of P tensor, one of these cocores. And now the cocores generate. So we can just replace this localization by the localization of the whole Fukaya category tensored with this chain complex. And finally, the claim is that quotienting it out, localizing by this subcategory is the same thing as inverting P. So let me explain this last inequality. Basically, forcing this chain complex to be acyclic is the same thing as making P be invertible. So the way that a chain complex is acyclic is when chain complex is when differential is when the differential is an isomorphism. So if you force that chain complex to be acyclic, you're making the differential, which in this case is P, be invertible. So this shows that the Fukaya category of X sub P is the localization, but away from this prime P of the Fukaya category of X. So yeah, this part is the main ingredient, I would say, is this Ganatra-Pardon-Shende result, combined with this construction of opposite incital. Are there any questions about this part? Okay, so that's the main construction. You carve out these disks, and this is what you get. Now, one thing that this perspective suggests, I mean, it shows that these X sub P's are actually subdomains. And so now you can ask, well, given a fixed domain, what are all subdomains of it? We know there's these X sub P's, but are there more? And recall this result that I mentioned with Sullivan, saying that all subdomains of T star M have the same Fukaya category as some of these X sub P's. So I'm going to talk about that in a second. So let's consider some arbitrary subdomain X of T star M. What that means is there's a Weinstein cobordism from the boundary of X to T star M. So you start with X, you attach a bunch of handles, and then you get T star M. Now, some of those handles are subcritical, and some of those handles are critical, and they have cocores DI. Now, if you remove those handles, which is basically saying you remove those DIs from T star M, you just get X plus some subcritical handles. And what that implies is that the wrapped Fukaya category of X is isomorphic to the wrapped Fukaya category of T star M, localized by some Lagrangian disks DI. So computing the Fukaya category of X just reduces to identifying which objects of the Fukaya category of T star M are isomorphic to Lagrangian disks. So let me mention this inclusion of categories. So we have.
And this is why do you take the large thing to be T star M, just for simplicity of computation?
Well, it's okay because the result is going to be for T star M, but this discussion so far holds for arbitrary domain. So we have this these embeddings of categories. So on the left, I have a category of disks consisting of objects that are actual Lagrangian disks and morphisms given by Rapp-Floer homology. Then we have the Rapp-Foucault category of T star M consisting of genuine Lagrangians. And then we have the Foucault category of twisted complexes, where we take this formal algebraic enlargement, and we're interested in the image of this embedding. So the question is, which twisted complexes are isomorphic to actual Lagrangians in X? Because you do this formal algebraic enlargement, and of course you lose some information. And let me just say that the benefit of this algebraic enlargement is that it's computable. Twisted complexes on the Foucault category of T star M is isomorphic to twisted complexes on the cotangent fiber, which is isomorphic to twisted complexes on chains on the base loop space of M. So the right-hand side is computable, but the cost is you've enlarged it. So let me state some twisted complexes and say what actual Lagrangians they're isomorphic to. For example, the zero section. So again, every Lagrangian is going to be a twisted complex of a cotangent fiber because the cotangent fiber generates. But the question is, which twisted complexes of a cotangent fiber are isomorphic to actual Lagrangians? So the zero section is isomorphic to twisted complex consisting of two cotangent fibers with differential given by a morphism gamma. And this gamma is some higher degree morphism living in, I guess, degree 1 minus n. But then we also have these Lagrangian disks that I mentioned. Like the D2 disk is just a twisted complex of two cotangent fibers with differential given by 2. When I say 2, I mean really 2 times the identity morphism. And this is a morphism in degree 0. And the distinguishing feature between these two types of twisted complexes, I would say, is that the twisted complex on the bottom is just kind of a good old Z chain complex tensor fiber. Whereas the twisted complex up top is some twisted complex that involves higher morphisms. And it's not just a Z chain complex. Okay, so those are some examples. And so I want to mention this theorem with Sullivan again, which is that if M is spin simply connected Lagrangian in T star M that is null homotopic, then it's actually isomorphic to just a Z chain complex tensor, one of these cotangent fibers. So we start off with this completely topological condition of being null homotopic, and we conclude a Floer theoretic condition that it's isomorphic to one of these Z chain complexes. So note that the zero section is actually not isomorphic to a Z chain complex tensor cotangent fiber. It involves this higher degree morphism. But of course, the zero section is not null homotopic. So this is compatible with the theorem that I'm stating here. And the conclusion is that let's consider the image of the Rapp-Foucault category of T star n, the cotangent Rapp-Foucault category of the cotangent bundle in the dimensional sphere into the twisted complex Foucault category. So this is an embedding. The question is, what is its image? And well, what are the Lagrangians? Well, there's either closed exact Lagrangians, and the only one we know is isomorphic to the zero section, or there's Lagrangians with boundary, and those all turn out to be null homotopic. Like any manifold with boundary in T star Sn is actually null homotopic, and so it's going to be isomorphic to one of these Z chain complexes, tensor fiber. So the conclusion is that not all twisted complexes are geometric. There's twisted complexes which are not in the image of this these actual Lagrangians. I mean, just for an example, you could take the zero section and then you could take the cone on like 5 or something. It's just a silly example. Well, you could look up any kind of twisted complex you want, and most of them will not be geometric.
Oleg, I have one question. This D, so in the result just above, if you can just slide a tiny bit above, so you had this, so D2 is embedded or not? And in this statement about L, you look at embedded things or immersed things? No.
Yeah, so everything here is embedded.
Embedded, all right, great. Because I mean, I think for this...
so this is embedded.
All right, excellent. Because I think, in fact, the expectation is you can represent twisted complexes using immersed stuff. So, but okay, that's a...
Right, so in that case, you need some extra... Yeah, in that case, you need some extra data, which is this bounding cochain, which...
Yes.
Okay, I can hear myself. I don't know if there's an echo. And so that's already, I would say, more algebraic data. Whereas I'm really considering just purely geometric objects, just exact Lagrangians, no bounding cochain, nothing.
Sure. I just wanted to understand
and then you have restrictions.
Yeah.
Yeah, I should have said that. That's right. Okay, so you got this restriction.
In the theorem, you're producing some geometric twisted complexes, but your upshot is some twisted complexes in the very bottom are not geometric. You have this cone of 5. How do you see it's not?
Yeah.
I completely.
Well, it's not geometric because you're not because it's the zero suction cone of 5 instead of like the cotangent fiber.
But that doesn't show it's not. Does it show it's?
Okay. Yeah. Okay. And then. Okay. I guess I didn't say this. There's some extra. Well. Okay. This previous theorem with Sullivan says that if you're null homotopic, then you're actually isomorphic to just a chain complex over Z. And okay. And then if you consider this thing with the cone of 5 of the zero section, this is not some. So okay, let me say that these ones that are null homotopic, they either have infinite wrapped Floer homology or 0 wrapped Floer homology, and this cone of 5 of the zero section does not have that property. There's some like a little bit of algebraic work maybe to show that this thing is not isomorphic to a chain complex tensor fiber. But that's almost immediate, I would say. And once you have that, you can conclude it's not geometric. Okay. Are there any more questions? Okay. Well, I think the next part was going to be a discussion of this like uniqueness theorem up to stabilization and subcriticals, but it seems like I'm out of time. So I think this is a good place to stop. And if people want me to talk about that later, I'd be happy to. So thanks for listening.
Thank you very much, Oleg. there any questions? Any further questions for Oleg?
Could you maybe explain a little bit more about those P-Moore spaces? And particularly the dimension constraint there.
Yeah, so let's see. Okay, so P-Moore space is what you get. So let me try to redraw this picture. P-Moore space is going to be U, which is a circle, and then you attach a disk to it that kind of winds around P times. So it's kind of a circle with a disk, so that the boundary disk is attached to the circle, going around P times. And so you have a CW complex with just 1 and 2 handles. And this, by the Whitney trick, this will embed in R5, which is sitting inside of S5. But so that's already close to what I said. But in fact, there's like an explicit embedding of this P-Moore space into S4, which you have to write down some formula, but you can do that. And so that's how you get the embedding. And I think you can show that this P-Moore space does not embed into S3.
So it's not something that's immediately obvious from the unembedded,
yeah, I think, this P-Moore space. Yeah, I mean, it's like saying like RP2 does not embed into S3. So it's some generalization of that. And so once you have this embedding, you take a neighborhood of it. So that's your domain U. And then this U is sitting in the sphere. You view that sphere as the boundary of a disk. And then you create a function on the disk, which kind of goes to negative infinity near U as you approach the boundary, and it goes to positive infinity kind of away from U. And there's some region between that where I think it stays 0. And so the point is you have this function from a disk to R that depends on U. So maybe I should say this function depends on U. And then you take the differential of this function, and that gives you a Lagrangian of T star dn. And it's a disk because it's just the graph of a one form over a disk. Does that clarify?
Thank you.
All right, so let's thank Oleg again for his talk.